Swayam Prabha. Digital India. Educated India.
So, now we will start the poles and zeros of a system. So, our topic is poles and zeros of a system, or you can say transfer function. Fine. Suppose this is the block diagram for a single input single output system GS. Input to this process is F bar S and output of this process is Y bar S. Fine. So, we can write this in this form, Y bar S divided by F bar S equal to G S. G S is the transfer function we know. Now, this transfer function is actually the ratio of two polynomials. The transfer function G S may be the ratio of two polynomials. One polynomial is Q S, another polynomial is P S. Fine. Now, what is the zeros of a transfer function? Zeros. The roots of the polynomial Q S are the zeros of the transfer function or the system. If Q S is a polynomial, then the roots of the Q S are the zeros of the system. Roots of the polynomial Q S are called zeros of a system or zeros of a transfer function. Got it? It is very simple. Q S is a polynomial. Now, we need to determine the roots of that polynomial, and those roots are zeros of that system or transfer function. In the similar fashion, roots of the transfer function P S are called poles of a system or poles of a transfer function. Fine. Now, we will take one simple example to explain the concept of poles and zeros. So, we will take next one example. We will consider the equation in S domain, that is say G 1 S F1 barish. This is the representation of the model for a seesaw system in Laplace domain, where G1 is given as k divided by S plus A. Fine. You can write this as Qs divided by Ps. Fine. But the numerator is basically constant. So, that is not the polynomial of S. That means there is no zeros. So, for this example system there is no zeros. Fine. And what about Ps? Ps is S plus A. So, there is a pole at S equals to minus A. Understood? There is no zeros for the example system and there is a pole at S equals to minus A. Now, one point I want to mention, that is, at the poles of a system the transfer function becomes what? At the poles of a system transfer function becomes infinity. Fine. Our pole is, the pole for this system is at S equals to minus A. If we substitute in this equation S as minus A, the transfer function becomes infinity, is not it? If we put S equals to minus A, then Gs becomes infinity. But the similar way we can say, at the zeros of a system the transfer function becomes 0. So, at the zeros of a system transfer function becomes 0. So, these are the concepts of poles and zeros. In the next we will discuss with the general form of transfer function. We will discuss the general form of transfer function. Fine. So, an nth order system we will represent by a linear ordinary differential equation. I mean, the process will represent by an nth order ordinary differential equation in linear form. So, that has the form a n d n y d t n plus a n minus 1 d n minus y d t n minus 1, like this, a 1 dy dt plus a naught y equal to b m d m f d t m plus b m minus 1 differentiation so b 1 df dm, sorry, this is dt, b 1 df dt plus b naught f. This is the general representation of a linear process, where all the a and b are constant coefficients and y f both are deviation variables. A and b, these are constant coefficients, y and f both are deviation variables. Fine. Now, if we take Laplace transform and rearrange, we get the transfer function, and that has the form of G s equal to y bar s by f bar s equal to I equal to 0 to m b suffix I and s to the power I. Similarly, here I equals to 0 to n a suffix I s to the power I, and we get b m s to the power m plus b m minus 1 s to the power m minus 1, last term is b naught. A n s to the power n, a n minus 1 s to the power n minus 1, last term is a naught. Now, if we take common b m divided by a n, we get s minus z 1, s minus z 2, s minus z m whole divided by s minus p 1, s minus p 2, s minus p n. Fine. This is the general form of transfer function. Here all z represent the zeros and p represents the poles. Z I denotes the zeros and p I represents the poles. Fine. Now, what about the order n and m? I mean, n will be greater than m or equal to n or less than m. For all physically meaningful system, n should be greater than or equal to m. For all physically meaningful system, n should be greater than or equal to m. Physically realizable systems, this term is used in process control. Physically realizable systems, I mean all physically meaningful system, n should be greater than or equals to m. You can test it. You consider n less than m and you check what type of response you are getting. Like for example, a step change in input variable produces an infinite spike in the output. If you consider suppose n equals to 0 and m equals to 1, then you give a step change in input variable f, you will see that there is an infinite spike in the output. For this reason, for any physically meaningful system, we have to consider n greater than or equals to m. Fine. So, next we will discuss transfer function and its analysis. transfer function and its analysis. One important point, I mean the use of transfer function we have discussed, that is to observe the transient behavior of a process, we can use the transfer function. Another important point, I mean the use of transfer function, is the stability analysis. Fine. To know the stability of a system, we can use the transfer function, that we will discuss in the next. So, we have mentioned earlier that this Qs divided by Ps, this is basically the representation of a transfer function. I mean the transfer function is the ratio of two polynomials, one is Ps, Qs divided by Ps. Now, we will take one general form of this transfer function, that is represented by this equation, Qs divided by S minus P1, S minus P2, S minus P3 whole to the power m, S minus P4, S minus P4 star, S minus P5. This is the general representation of a transfer function. Fine. Now, S is basically a variable which is defined in the complex plane in this way. I mean this is the form of S, S equals to A plus JB. Fine. S is defined in the complex plane by this form. Now, considering this general form of a transfer function, we will discuss different types of poles. For example, one system which has two poles, they both are real, but distinct. In another case, we will consider a system which has multiple poles and all the poles are real. What about the stability of that system? One system which has two complex conjugate poles, what about the stability of that system? Like this, different situations we will consider, and all these poles are included in this general form. So, first we will consider distinct real poles. So, in first case we will consider real distinct poles. Fine. Now, to consider this case, we will reduce this general form of the transfer function to this expression, Gs equal to, anyway we can take the partial fraction of this equation before considering the different cases. So, we can write this equation in this way. So, C1 S minus P1 plus C2 S minus P2 plus C31 S minus P3 plus C32 S minus P3 whole square, like this way, C3m S minus P3 whole to the power m plus C4 S minus P4 plus C4 star S minus P4 star plus C5 divided by S minus P5. Fine. This is if this is the partial fractions of this transfer function, general form of the transfer function. I think I am writing again that G s equals to C 1 s minus P 1, C 2 s minus P 2 plus C 3 1 s minus P 3, C 3 2 s minus P 3 whole square, last term is C 3 m s minus P 3 whole to the power m plus C 4 s minus P 4, C 4 star s minus P 4 star plus C 5 s minus P 5. I have written that general form in this equation. Fine. Next, we will consider the first case, that is real distinct poles. So, in case 1 we will consider real distinct poles. In this case, we will consider just the two poles, both are real and both are distinct. Those two poles are, one is P 1, another one is P 2. Fine. So, the general form of the transfer function reduces to G s equals to C 1 by s minus P 1 plus C 2 by s minus P 2. Can I write this? We are presently considering a system which has two distinct real poles, and these poles are P 1 and P 2. So, we are considering just this part of the transfer function. Fine. I have mentioned another thing, that the S is defined in the complex plane by S equals to A plus J B. So, we can represent these two poles in the complex plane in this way. Suppose this is real axis, this is imaginary axis. So, both the poles are real and distinct. So, one pole we will consider in this side, I mean the left hand side of this imaginary axis, another pole we will consider right hand side of this imaginary axis. Fine. One pole is in the left of imaginary axis and another pole P 2 is in right of the imaginary axis, and the transfer function is represented by this equation, G s equals to C 1 by s minus P 1 plus C 2 by s minus P 2. Now, if we take the inverse of Laplace transform, what we get? Inverse of Laplace transform, we get C 1 exponential of P 1 t plus C 2 exponential of P 2 t. If we take the inverse of Laplace transform, we get this expression. Fine. Now, if P 1 is greater than 0, P 1 we have considered in this complex plane, sorry, this P 1 is less than 0, because that is in the left of imaginary axis. So, P 1 is less than 0. If that is the case, then C 1 e to the power P 1 t, I mean exponential of P 1 t tends to 0 as time tends to infinity. Can we write this? We have considered P 1 less than 0. So, exponential of P 1 t multiplied by C 1 tends to 0 as time goes to infinity. We can represent this graphically also. It is like this, going to 0, this is t, this is C1 exponential of P1t, fine. In another case, we have considered P2 that is greater than 0, then C2 exponential of P2t tends to infinity as t tends to infinity. Agree? If P2 is greater than 0, then C2 exponential of P2t goes to grows to infinity as time tends to infinity, fine. So, we can say that if a system has the pole in the left of imaginary axis, then the system is decaying to the 0, that means the system is stable. And if the pole is greater than 0, in that case it is growing exponentially towards infinity, that means the system is becoming unstable, fine. Fine. In the second case, we will consider the multiple real poles. In the second case, we will consider multiple real poles. That pole is here P3 and that is repeated m times, fine. We will consider multiple poles represented by P3. So, first you will locate that P3 in this axis complex plane. So, suppose one P3 is here, this is one P3, another P3 is suppose here, fine. Like this way P3 is repeated m times, and for this multiple real pole system we will consider the transfer function represented by C31 s minus P3, C32 s minus P3 whole square, like this. Last term is C31 s minus P3 whole to the power m. If you see the general expression of the transfer function, that is this is the general expression of the transfer function. Now, to consider the multiple real roots, we are considering this part as the transfer function, that I have written there, fine. So, Gs equal to C31 by s minus P3, C32 by s minus P3 whole square, like this way. This is C3 m divided by s minus P3 whole to the power m. In a similar way, we will take the inverse of Laplace transform Gs. So, what we will get? C31 plus C32 divided by factorial 1 multiplied by t plus C33 divided by factorial 2 multiplied by t square, like this way. C3m divided by factorial m minus 1 multiplied by t to the power m minus 1. This will be multiplied with exponential of P3t. If we take the inverse of Laplace transform of this transfer function, we get this. Suppose I am writing this as W multiplied by e to the power P3t. I mean this whole part this one we are representing by W, fine. So, next we will consider P 3 greater than 0, P 3 greater than 0, then exponential of P 3 t grows to infinity, agree, as t tends to infinity. So, what about W multiplied by e to the power P 3 t tends to infinity. That means, again instability problem is there, because the system response is going to infinity. In another case, we will consider P 3 less than 0, P 3 less than 0, then exponential of P 3 t tends to 0 as t tends to infinity. So, what about this W multiplied by exponential of P 3 t? It will decay to 0, fine. And in the third case, if we consider P 3 equal to 0, exponential of P 3 t becomes unity, exponential of P 3 t becomes 1 as t tends to infinity. So, what about this W multiplied by exponential of P 3 t grows to infinity due to this W grows to infinity as t tends to infinity. So, due to this term we are getting this W multiplied by exponential of P 3 t becomes infinity, fine. So, these are basically the different real roots associated with a process and the stability of that process. Now, in the next case we will consider the complex conjugate poles, that is the third case. In the third case we will consider complex conjugate poles. So, for the complex conjugate poles, we will consider the third portion of the general form of transfer function. The general form of transfer function, I am again writing that C 1 s minus P 1 plus C 2 s minus P 2. These two right hand terms we have considered for the two distinct real poles. Next term we have considered for the multiple real poles whole square 3 m s minus P 3 whole to the power m. So, now we will consider this part C 4 divided by s minus P 4 and C 4 star divided by s minus P 4 star, and in the fourth case we will consider C 5 divided by s minus P 5. This we have already considered for the distinct two real poles. This part we have considered for multiple real poles. Now, we will consider this part. I mean the transfer function reduces to C 4 S minus P 4 plus C 4 star S minus P 4 star. Fine. Now, the two complex conjugate poles are P 4 and P 4 star. So, we will consider P 4 equals to alpha plus j beta and P 4 star we will consider that is alpha minus j beta. Fine. These are the two complex planes, two complex poles. Now, we have to represent them in the complex plane. This is the complex plane, this is real axis, this is imaginary axis. Suppose one pole that is P 4 and another pole that is here P 4 star. Fine. So, this is alpha plus j beta and another one is alpha minus j beta. Now, as usual we need to take the inverse of Laplace transform. If we take the inverse of Laplace transform, the right hand term includes one exponential term, exponential of alpha t, and one sine function, that is beta t plus phi. Fine. The right hand term includes one exponential function, exponential of alpha t, and another one is sine function. Now, this right hand term may be multiplied with some value, suppose w. Fine. So, next we will consider the different situations, I mean different values of alpha. Then what will be the response of the process having two complex conjugate poles. So, in the first case we will consider alpha greater than 0, alpha greater than 0. If alpha greater than 0, then exponential of alpha t tends to infinity as time tends to infinity. Agree? Then what will be exponential of alpha t multiplied by sine beta t plus phi? It grows to infinity in oscillating manner. It grows to infinity in an oscillating manner. Fine. It is going to infinity in oscillating manner because of this sinusoidal function. So, how we can represent the system response graphically? So, we will represent this in this form. Suppose this is time and this is output function, this is output. Initially like this. So, initially the process was at steady state, fine. Now, we have introduced some input change, then the output responds in this manner, it is going towards infinity. So, it is obvious that if alpha is greater than 0, the system has instability problem, fine. Similarly, we will consider alpha less than 0. In the next case, we will consider alpha less than 0. Then e to the exponential of alpha t tends to 0 as time tends to infinity. So, exponential of alpha t sin beta t plus phi decays to 0 in an oscillating manner. So, it decays to 0 in an oscillating manner. The graphical representation is like this. This is the time, this is output, so it is gradually stabilizing. I mean the process is coming back to the original state, fine. And next we will consider alpha equal to 0. If alpha equal to 0, then e to the exponential of alpha t equal to 1 as time tends to infinity. So, exponential of alpha t multiplied by sin beta t plus phi what will be the response? Sinusoidal with, sinusoidal, I mean in constant amplitude. So, we can write it oscillates continuously with constant amplitude. This is sometimes called marginally stable. This is sometimes called marginally stable, and for this case the graphical representation is okay, fine. This is time, this is output, like this. This is the case for alpha equal to 0. So, we have considered 3 different cases. Now, another case, I mean the last case in which we will consider this transfer function, fine. This is the first case, second case, this is the third case, complex conjugate poles, and this is the fourth case. In the fourth case, we will consider the pole is at the origin. So, in the fourth case, we will consider poles at the origin. I mean, if we draw the complex plane, this is real and this is imaginary, the pole P5 is present here, this is P5. That means P5 equal to 0, or we can write in this form 0. Then transfer function Gs reduces to C5 S minus P5, this is P5 equal to C5 divided by S, fine. Now, we will usually take the inverse of this Laplace transform, then we get C5, one constant term, fine. So, these are the 4 different cases which we have considered here, and we have we can conclude based on these 4 observations, I mean considering the 4 cases, that a system is said to be stable if all the poles lie in the left of imaginary axis. This is our conclusion based on the 4 observations. A system is stable if all the poles of its transfer function lie in the left of imaginary axis, fine. And in the subsequent chapters, we will study more about the stability, considering different techniques. Now, we will take one simple example, one simple transfer function which we have considered earlier. One simple transfer function we will consider that we have discussed earlier, that is Gs equals to k divided by S plus A, fine. So, this is a stable system or unstable system? Stable system. Why this is stable system? Yes, because S is equal to minus A. So, if A is negative, not stable. So, here one pole exists at S equals to minus A. So, we can say the system having the transfer function of Gs is stable only if A is positive, fine. If A is negative, this is unstable, because in this case the pole lie in the left side of the imaginary axis, and in this case the pole lie in the right side of the imaginary axis. Another example we can consider, that is the liquid level system. For the case of liquid level system, we got the transfer function that is one divided by A s f I bar prime s minus 1 divided by f s f naught bar prime s. Fine. And this model we got considering this system f I and f naught. Fine. A is the cross sectional area and h is the height. Now, we can do one thing, we can consider f is proportional to h. We are just trying to modify this example. Fine. Now, f naught equals to suppose alpha multiplied by h. Fine. Now, if we substitute this in the model equation, then what we will get? F dh dt equal to f I minus f naught equal to f I minus alpha into h. So, f dh dt plus alpha h equal to f naught f I. If we write in terms of deviation variables, we will get alpha h prime equals to f I prime. Fine. So, what will be the transfer function for this? H bar prime s divided by f I bar prime s equal to 1 divided by s a plus alpha. Can I write this? 1 divided by s a plus alpha. Agree or not? Agree. So, what is the root? I mean, what is the pole of this equation? Minus alpha divided by a. So, the system is stable or unstable? The system is stable. Area is always positive. So, if we consider alpha is positive, then the system is stable. Okay, thank you.